We have a few participants who already joined. More will join, but I can begin with your introduction in the interest of time. So,
Sure.
hello
Yeah, sounds
everyone.
good.
Thank you for joining. Today with us, we have Ekanshdeep Gupta. Ekansh is at New York University, and he's a final year PhD student wrapping up his thesis. His work is on separation logic. In particular, he's going to talk about Raven, which is an intermediate verification language for concurrent separation logic. Over to you, Ekansh.
Yeah, hi, Alok. Yeah, hi, everyone. Thanks for the introduction. Um, oh, sorry, I forgot to update the date. Yeah, it doesn't matter. Yeah, so yeah, thanks for the introduction. Like Alok said, I'll be presenting Raven, which is the main sort of focus of my PhD. So yeah, yeah, I think we can just get started. A few housekeeping things. I don't see the chat, Alok, so if you could just let me know about any comments there, etc. I would also like this to be interactive and yeah, participation, interruptions, clarifications are always welcome. Um, my understanding is that it is a little bit of a diverse audience, so if there are confusions or things, etc., like yeah, feel free to pipe up and we can take it as it happens. And I assume like Alok will sort of mediate that as well. And
Yes,
yeah,
so
uh,
if you are okay with it, Ekansh, people can unmute themselves and ask you questions during the talk,
perfect. Yeah,
or
yeah, that would
I can
be.
moderate it on the chat, or we can take them at the end, whatever you prefer.
I would rather do it as it like as we go along because yeah, at the end, like going back and forth with the slides would be a bit annoying. So yeah.
Sounds good.
And yeah, I'll also keep a time check for myself. But yeah, if you could give me like a 15-minute heads up, I can start wrapping up in 5 minutes and have 10 minutes for questions.
I'll do that.
Yeah, of course. Okay. Yeah, with that, let's begin. Yeah. So, like Alok said, this is primarily about concurrent separation logic, which is a program logic that has been developed, worked on for since 2001, I want to say. But yeah, whatever, doesn't matter. Right. And the problem is, I mean, the problem that concurrent separation logics are trying to solve is how do we actually go about reasoning about concurrent data structures or concurrent programs in the presence of a very high amount of concurrency, right? Like you want to prove properties like linearizability, but yeah, you don't want to have to deal with every single interleaving of all the different processes. And of course, I mean, this slide is just to sort of highlight the kinds of problems that people run into. I mean, real world issues happen because of these problems. And in fact, this is like a funny example of, my advisor. There must have been some issue or whatever with the system, and they disburse the payment twice and so on. And it's not just like mortals, like normal programmers, even experts make mistakes, right? The art of multiprocessor programming is like the bible for concurrent data structures, etc. But of course, I mean, no one is immune to making errors and so on, and so there have been errata and corrections and so on afterwards as well. Okay, so yeah, now that I guess, I mean, I hope to have convinced you of the importance of this endeavor. I think I can start with defining separation logic formally. Yeah, so 2001, 2002 is when it sort of started picking up steam, right? And so a whole Hor triple is something that I assume everyone must be familiar with. It's basically it's a triplet. So you have a precondition denoted by P here, a program or a command, and then a postcondition Q, right? And a hot triple being valid means A, that C executes without failure from any state that satisfies P, and moreover, if C terminates, so this part is crucial because we don't we only talk about like we don't consider we don't have termination proofs etc in Raven. I mean, that can be added with with not too much effort, I think. But yeah, I mean, we talk about like functional correctness, not like total correctness. So if a program does not terminate, then we can just prove false here. If we can prove that a program does not terminate, then the post condition can be false because the this condition is never satisfied. Okay. Yeah. Okay, so basically, things we need to understand, we need to know the language of our propositions, our assertions, sorry, what kinds of programs we have, and then what sort of proof rules are allowed in our program logic, right? Yeah, so, okay, so let's start with that. The kind of program assertions that we yeah, so sorry. So the key feature of separation logic is a points to predicate. Um, in Hor logic, we would say something that, oh, x dot f equals to y. Whereas here we have that x dot f points to y, which expresses a certain notion of ownership. Okay. And similarly, if we do that, oh, y dot f points to y, then it would be like a loop, like a self-reference, right? And now the question is, well, if I have x dot f points to y star x dot f points to z, then or z, what would this heap shape correspond to? In the interest of time, I mean, I won't sort of wait for answers. The answer, I mean, this is standard stuff as well. Is that it is unsatisfiable, and the reason is because, yeah, so x dot f points to y star x dot f points to z. Um, the way that you would satisfy such an assertion is you would split a heap into two subheaps, and one subheap should satisfy the left conjunct, and the other subheap should satisfy the right conjunct. And importantly, these subheaps have to be disjoint because, like I said, the points to expresses a certain notion of ownership, right? So x dot f can't be in two different places at once, which means that this is not satisfiable because, like I said, there's no way to split the heap into disjoint pieces that satisfy both of these. Okay. And well, one thing that Raven supports is you have, oh, sorry, I guess I should have mentioned this earlier, is that you have typed fields and then you have references. So X is a reference and F and G here are fields, right? So this is satisfiable because you can, you know, separate the heap into like this chunk and then this chunk. Um, yeah, I mean, basically, the values at, sorry, so x dot f and x dot g represent some blocks in memory, and you can just separate those out. And x is just a reference to, yeah. Okay. Yeah. So then I guess the next thing is, so we have one of the sort of like primitive for the assertions. I mean, I guess that is sort of all the assertions. You have separating conjunctions, you have points twos, um, and that's, I mean, you can add the standard conjunction and disjunction, etc. But typically in separation logic, that is kind of not needed, and it makes things more complicated. In fact, so separating conjunction, as the star is called, is the standard operator. Okay. Now, yeah, I mean, okay, so then just to go over the semantics briefly, we have references, we have values, which is, references, integers, booleans, some standard set of data structures. Fields, like I mentioned, are the typed fields. This is heavily inspired from, Viper, for instance, which is a project from ETH Zurich. And they also have a similar notion of references and fields, and then of course we have an infinite set of variables and things like that, right? Okay, so then the semantics are, a state is a pair of a stack and a heap, right? And a stack is, I mean, this is all standard stuff. I'll not bore you with the minutiae. Right, and this is the formal definition of what it means for what the formal definition of the semantics of the separating conjunction is. So basically, we say that this sort of state refers to you take a disjoint union of the heaps. And if the stacks are disjoint, then if the stacks are different, then I mean, I guess those states are incompatible, so you cannot do a separating conjunction of those. But if the heap lets sub heaps are disjoint, then you take the disjoint union. Okay. Yeah. And then, like, yeah, a state comma heap satisfies points to if you look at the variable, it's in the domain, whatever, whatever. It satisfies p comma q, p star q if you can separate it into two states. And yeah, and the rest of the things are, yeah, I mean, you have all the sort of basic first order things as well. And then just to quickly go over the program syntax. On the left is the set of basic commands that we offer. So we have a no op, a guard. You can write to the heap, read from it, allocate new memories. I think I'm forgetting. Like we have one like to spawn new threads with a certain like executing certain functions, etc. But yeah, and then uh, yeah, and then on the right we have like the full command language. So we have the basic commands. We can of course also sequence them. We have non-deterministic choice, looping, and like spawning threads, like I said, etc. I think I'm missing one or two maybe, but not much more than that. Okay, so then yeah, just to sort of cover my bases. I mean, no formal method stock is complete without all of these operational semantics, etc. Yeah, so I mean the reduction relation, yeah, it takes a step in sigma, yielding whatever sigma c prime and a new state sigma prime. And just to sort of make it slightly more concrete, if we have x dot f equals y as the command, and we start from a sigma state, then we would go to this would become a no op if the command can be executed, and sigma prime would be defined as yeah, as this, where we do the update. And if it's not valid, if we don't have, basically, yeah, if we don't have permissions to x dot f in our state sigma, then that's an error state and we abort, and yeah, the program crashes basically. Okay. Uh, I mean, this is all stuff we've gone over. Yeah, the meaning of a hot triple, states. But yeah, I mean, this is just written formally if something else. Okay, so we have gone over the commands, we've gone over the assertions. The last thing is separation logic proof rules. I would assume I mean, I don't think anyone would be too surprised by any of these. Yeah, you have allocate, read, write, sequence, etc. Right? And then the one very crucial rule, which is unique to separation logic, is the frame rule, right? And what that means is given any P, C, Q, hot triple, you can add an arbitrary frame to it, right? And um, yeah, you can add any arbitrary frame to it. And the reason this is fine, this is allowed, this is safe in separation logic as opposed to standard HOR logic is because we like having P here gives us ownership or like exclusive access to the resources in P. And the semantics of the separating conjunction make sure that the F that we pick cannot intersect with P and cannot interface with P, and also that the command C cannot interface with anything in F because we already have this hot triple, right? So C cannot access anything that's not explicitly mentioned in P. So C can't influence F, F can't influence P, etc. So you can just add any arbitrary frame surrounding it, and you can, as long as that is unchanged, you can go from P to Q and so on. So this is like the foundational sort of rule. Um, yeah, we're at 20 minutes right now. Okay. Yeah. So this is an example proof. I might just go through it quickly. So suppose you want to prove this specification. We're allocating two values and then setting something to one. F is the name of the field and 0 is the initializing value we give. Oh, by the way, sorry, I should just clarify that all the code in this talk is, like Raven syntax and valid Raven code. I'll of course get to that later, but yeah. So f is a field, 0 is the initialization value. We do this. So first we apply the sequence rule. We start from true and we say that there is some r for which we can apply the sequence rule, right? And the question is, what is r? So I mean, yeah. So we set r to this. Allocate. So now we're here. We've dispatched the first statement. Now we're here. We again do the sequence to break it into two. Again, we use the alloc. And now we use the frame rule to basically use. Okay, so basically we set f here to be the first like x dot f points to 1, right? So this is f, and we use the frame rule, yada yada, and then this is the standard, right rule. But notice that again, to derive this, we could have defined the right rule in a more powerful manner, where we have a frame, arbitrary frame here, but we want to keep our proof rules as simple as possible, and we would explicitly evoke the frame rule to go from this to this, and then evaluate the right rule here. Okay, I think that sort of covers the all the things that I have to say about separation logic, like concurrent separation logic, etc. If anyone has any doubts, I think this might be a good point to stop and answer some questions.
Yeah, some separation logic that I've seen has this
Mhm.
the bond rule, the bond operator,
Yes, the magic wand, it's called. Yes.
the magic wand or whatever. So
Mhm.
you don't have that here, is it?
We do not. No, in Raven, we don't support the magic wand because it sort of blows up the complexity of the first order encoding.
Hmm.
And also, like in our experience, like of course it's useful to have the wand, but we've been able to sort of work around the magic wand, and not really, it hasn't been a blocker in all the sort of data structures, etc., that we implemented.
You
Yeah.
don't think that will limit your expressive power in the kind of pointer programs that you could use, like recursive lists and so on and so forth?
Um, so Raven does have some features to sort of ameliorate the situation, like in the sense that give us some of the power back. In particular, Raven has a sort of very powerful higher order module system, which I mean basically it's like a functor. You can define functorial modules and so on. Yeah. So sorry. So to answer your question, yeah, we have not come across situations where that would be a big impediment.
Okay.
Mhm. Uh, okay. If there's nothing else, then maybe I can just proceed. Okay. Yeah. I mean, okay, so this is again some more sort of context just to build it up again. By looking at actual code. Of course, this is all valid Raven code. So just to start with something simple, something everyone's familiar with, we start with the sequential stack. The code should be pretty straightforward. When we push, we allocate a new location. We set the head to that, and then I mean, basically, yeah. And then the pop again, if it's null, we return none. It returns an int option type, which is a type that we have defined explicitly. Although now, I mean, this is the screenshot is a bit dated, but now we can just actually write option, square brackets in etc. Like option now is an inbuilt higher order type, etc. But yeah, sorry. So if it's the list is empty, we return none. If it's not, then yeah, we just do whatever the standard thing. One thing to note is we assume garbage collected semantics, so we don't necessarily explicitly free the thing, and that is also because it sort of fits more naturally with the concurrent separation logic. Although I mean there are projects like Refined C and others that deal with explicit memory management. But for Raven, we decided to not have to model that. Okay. So now, of course, this is a sequential stack, push pop, right? Everyone learned this in like their first year of undergrad. But then the question is, what happen? Like, if multiple threads want to execute, sort of want to operate on the same stack. Like, I don't know. Imagine, there's some counter somewhere that tracks how many followers I have on Instagram, right? Somewhere on Meta servers, and people would want to increment or decrement that counter, or like the list of my followers, etc. Right? And you can't just have one thread doing it for 50 million people, etc. So yeah, so okay, so just to highlight the problem that would be there if we just run push in multiple, this thing is that the incrementation, the update takes 2 clock cycles, right? So first we allocate a new memory, sorry. Um, yeah, basically in the what we need to do is we need to set the value um in the same step. So here one step is reading what s.head is, right? Then and the second step is, so I mean we can assign this earlier as well, right? Without interfacing with other threads. But the 2 steps that are still there, 2 hardware primitive steps, is reading the head and then comparing the head and then wanting to update it. Because and the reason we don't need to compare it here is because we are in a safe mono thread environment, so no chance of it getting updated behind our back. But yeah, when we do a concurrent thing, we have to perform what's called a compare and swap operation. Right, and Raven has like comes with a bunch of these built-in hardware primitives. You can also define your own, which is one of the sort of follow-up works which I'll talk about briefly, time permitting. Right. Okay. So maybe I'll just speed through this. So yeah, Triber stack is the data structure, which is like a standard multi sort of concurrent structure. And the key sort of design pattern that occurs throughout concurrent data structures is this idea of performing, a hardware atomic step. And then if that succeeds, we're done. Otherwise, what we do is we just have to yeah, sorry. In the push thing, if we succeed, then we return. Otherwise, we just do it in a loop till we succeed, right? So if we fail, what happens is that there was some other thread conflicting with us, and they won the race, whatever the race condition, and then we failed, and so we'll just try again till we succeed, essentially, right? And this does lead to some reduplicated effort, but I mean, it saves so much time because you can have, many, many, many threads all contesting. And then eventually, and also you do keep making progress, right? So eventually it'll all be fine. Okay. So now the question is, how do we guarantee correctness for something like this? I mean, of course, you can have all the standard engineering things, randomized test generation, use better languages. But what we are interested in is functional correctness because, like I said, we want to be able to say with high confidence that no matter what state our data structure is in, it won't crash or lose data or any other thing happening, or any other unpleasant things happening. So what we want to do is we want to prove what's called linearizability. um, for that we need these notions of program logics, etc., that I talked about earlier. Right, okay. So then and so the problem with these existing program logics, etc., is that they're mechanized in these interactive theorem provers like Lean or Rock or Isabelle, etc., which is very tedious to work with, and you can't expect like a normal program. Like, you need PhD students and professors, etc., to work on them, and you can't expect like a normal programmer to pick up. I'm not saying Raven can be picked up by a normal programmer, but it's much closer to that effort. And with building other tools around Raven, that is much more possible than trying to write a wrapper around Lean to get people to use it, etc. Okay, so yeah, so typically the way it works is Raven is an intermediate verification language, which means that we people build other people build user facing verification tools on them, right? And almost inevitably, all of these user facing tools, they use some intermediate verification language, because without it would be a pain to sort of have to write the entire sort of translation to first order logic by hand. And separation logic and intermediate IVLs basically just give you a nice interface to program against, so you don't have to straddle too many layers of abstraction at the same time. Okay. So yeah, I mean, just to sort of give a timeline, 2003 we had Y3. I mean, in 2003 we had Y, and eventually they came out with Y3, I think, which is the latest. Boogie, this MSR project. I mean, yeah, lots of lots of people involved, like Shaz Kadir, I think, is the main person sort of maintaining it even now, etc. Viper, as I mentioned already, ETH Zurich 2014. Civil is basically um, it is very closely baked into Boogie, and it uses certain attributes, etc., to perform refinement proofs, like layered refinement proofs, right? And then in this sort of picture, 2025, we released Raven. That's Edgar Allan Poe, if anyone's not aware. There is the magic wand in the logo, which is slightly ironic because we don't actually have magic wands in the tool, but yeah. Okay. So to sort of give you a picture of the trajectory, Boogie came out in 2005, and it provided standard hot logic, but without any notion of heaps or concurrency. Then Viper came along. It is built on a stronger logic called implicit dynamic frames, which is actually synonymous. I mean, equivalent to concurrent separation logic. There's a paper which explicitly formally shows equivalence. And then for heaps, they added, fractional sharing, which is this notion of multi-reader, single writer access. So, you have, so a heap location has a fraction of 1. If you have, say, 0.1 or anything greater than 0 but less than 1, you're allowed to you're allowed to read from it. And if you have whole like 1.0 ownership, you're allowed to write to it. It also doesn't have any notion of. So, I mean, the problem with this notion of heaps is that it is fairly limited, right? It's not customizable. If I want a different notion of heaps, you can't do anything about it. You have to sort of work with the constraints of the system. And the constraints are very deeply embedded in the design of Viper. Like it won't be easy to just open that up to be customizable to the user. And of course, they don't have any notion of concurrency. Civil is slightly unrelated to these things, but yeah, it's atomicity abstraction via layered refinements, and yeah, they have linear maps, which is, I guess, the theoretical underpinning of Rust as well. And then Raven, we have Iris style concurrent separation logic. Iris is a higher order concurrent separation logic framework. So we basically take Iris and we reduce it to, we curtail the higher orderedness in a lot of ways. And then we have, this system of higher order modules in Raven, which gives some of the expressivity back. Of course, not everything, because that would be intractable. And then the other thing is, yeah, generalizable host heaps. Concurrency is baked in, like I said. Okay. Yeah. Okay. I guess I can do a demo now. Not this. Not this. Sorry. Sorry. Yeah, I hope the text is visible. I can make it slightly bigger if needed.
It's visible.
Okay, yeah, thanks. Right. Okay. So this is sort of the current state of Raven, right? So we have a VS Code extension. You get verification successful, etc. Before we get into the code, I mean, I'll just show you if I do something stupid like that. You get verification failed, and you also get the location at which it failed. So post condition may not hold at this return point, and in fact, it is this assertion which does not hold, right? Okay. So basically, what this data structure fork join resource is a data structure which allows you to split off, like spawn off new threads. I mean, fork join is again like a very standard thing. I'm sure everyone's aware. You fork many different threads, and then at some join point, you want all of them to get done with their whatever computations, etc. and then you want to join at some point, right? And I guess there are a few important things that one should know about it. Actually, maybe just let me do a simpler example. Okay. Okay, this is a counter, much simpler. You can see that like whatever, 50 lines of code, right? Increment is a procedure to increment. So it's a counter that only goes up. I mean, yeah, it's you only have the increment and then you have the read, right? Um, okay, so to prove linearizability, we have these atomic preconditions and atomic postconditions using this atomic keyword. And that changes the semantics of the postconditions and preconditions slightly. Basically what that means is you have to do a bind AU, which I mean I won't get into the details of it, but essentially anytime that you have to access the precondition, you have to you do this open AU command. So basically you don't get access to the precondition right away, as you would imagine in like a sequential condition in a sequential setting. And that's precisely because other threads also want the same resources and you can't just hoard them for your entire run. So whenever you need a resource, you have a resource in the precondition, you have to do an open AU, which gives you the resource. Then you do some other ghost command. I mean, that's allowed, and then you are allowed to execute one atomic primitive, right? So this is like a read, right? And then you're either forced to abort AU. If you're not at the linearization point yet, you would abort it. Um, and then eventually you want to commit the AU. And sorry, if I sort of, for example, skip this commit, and I mean, so this is a different error, which is saying that inconsistent atomicity states. But if I also commit this one, then we get a different, wait,
Yeah, may I ask a
error.
question here? Yeah.
Of course.
Yeah, no. Maybe I missed something. I don't understand what kind of concurrency model you're using. What is happening here concurrently? And I mean,
Yeah.
you talk about linearizability, but
Yes.
linearizability of what operations on what data? I mean, so I'm confused about what is happening here. It looks like a
Okay.
sequential code to me with different methods. I mean, what is happening concurrently?
Right. Okay. Yeah, that's a great question. Um, yeah. So I guess. Mhm. Okay, I think what would be illustrative is also showing, a client for this data structure. But yeah, to sort of answer your question, the idea is that you know we would package this up as a library, right? I can just like it would look like this module count inc whatever, and then I will just close it here, right? Yeah, so basically this would be like a package. And then you would have other like clients interfacing against this, and the idea is that the clients can run each of these methods in, I mean, not the predicate, that's a predicate, each of the procedures concurrently in highly concurrent settings, let's say. And we want to say that the specifications that we have here do continue to hold. So for example, for increment, we say that this increment procedure atomically goes from counter xv to counter xv plus 1, where counter basically just has the ownership. Like so own is the points to predicate that I talked about earlier. Yeah.
Mhm.
So basically this is saying that the value at x dot c is v. This says that the value at x dot c is v plus 1. And the atomic means that increment does this atomically. So I mean, this is an innovation in, I think it was first in the Tada logic, where they have this thread modular way of proving linearizability by ensuring that all your operations are atomic, like in the manner that I just described, where you have to open and abort or open and commit, etc. Does that answer your question? No. Yeah.
Yep. Yeah, I guess partly. I mean, what you're saying is there are multiple clients that are trying to invoke
Yeah.
some of these operations in parallel, and you want to make sure that the data is consistent, okay, as per some linearizable thing. And in your proof, you limit the number of clients, or what are you? I mean, you in any given thing you fix the number of client processes that are trying to simultaneously do, or is your proof parameterized with respect to?
Yeah. So okay, that's a great question. Basically, the idea is that we actually don't really care about the number of client threads, etc. Um, right. The idea is that we are able to do a completely, thread modular proof of linearizability. That's kind of the really, the striking, like the important thing. Right. So because we do this, we maintain this strict discipline that, oh, we don't have access to the precondition. Whenever we want it, we have to open it. And then after, okay. So for instance, if I just do this, um, right, it says attempting to take more than one atomic step with an open invariant or atomic update. So this is an atomic update that is opened. So AU is atomic update, right? And then if we try to do two steps, then there is I mean, Raven will complain and like shout at you that, oh, this is not allowed. You're breaking the sort of the contract of linearizability. So because of this, it doesn't matter how many threads there are in the client or how many clients there are, etc. We are able to perform, a completely thread modular proof of
Okay,
linearizability.
okay, I got it. Yeah, so you can have
Yes. Yeah.
a
Yeah.
copy of invocations of these things, regardless of
Of
things.
course.
Yeah.
Yes. Totally. Yeah. Uh. Yeah. Okay. I think we're also 20 minutes out from time. I think okay. So I think this sort of should give you an idea. Um, and also, I mean, this was. I mean, we discussed the Triber stack. Okay, maybe I should have just opened that. Uh, yeah. Okay, so basically, this is the Triber stack. This is the actual interface. We have stack, which takes a type, right? So this is the library, and then you would have clients that instantiate this module. Okay, so I would do something like module client one equals stack in type. Library dot type is it? Yeah. Okay. Yeah, and then I can do something like uh, yeah, sorry. Uh, yeah, I mean, basically, yeah. So we have a client now. Um, sorry, this should be stack in, right? And then the way this would happen is we have a module client, and you would have module si equal whatever stack in, and then you can execute si dot whatever dot 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 and so on. Okay. Uh, yeah. Okay, so that's the client. Again, maybe just to sort of go over the data structure, etc. I'll also just move on from this because of time. We have a predicate list, right, which does the standard thing of it either has so basically it says that you have ownership over the head and ownership over the the sequent of the list. We have a stack. The push procedure, again, you have atomic specifications. You see open AU, abort AU, host commands, host variables, host values. Then the cas, if this succeeds, then we commit, otherwise we recurse. And then when the recursion succeeds, then we commit in the other case. Right? Pop goes this way, and so on. Okay. So yeah, if there's no more questions, I think I'd like to get back to the talk and like go over the final few slides. Uh, okay. Oh, Okay. Okay. Yeah. Doesn't matter. Yeah. I mean, there's a QR code if and a URL if anyone wants to try it out. You can also just Google Raven NYU, whatever, it will show up. Or my advisor's name, anything. Okay. Just to sort of talk about the tool quickly. The idea is that Raven, is a few different components. So we have the Raven IVL, which is just the language, and then we have the verifier, which is all the sort of rewrites and all the encoding of separation logic into first order logic, etc., etc. Um, and so the verifier takes whatever comes through the Raven IVL and translates it into an SMT backend. We use Z3 because that was just the easiest, whatever. And we also have the Raven front end language, which is what I demonstrated just now, right? So you can use Raven as a full-fledged, tool, just like type, like write, like as a full-fledged like programming language. Although of course you don't get executable code. But yeah, so the idea is that you build other front ends, which similar to other IVLs like Boogie and Viper, other front ends which would use Raven as an IVL. And we already have, this is not my project, but someone is working in our lab working on developing such a Rust front end for Raven. And then, of course, there are other things. Okay. So yeah, so some qualities, some aspects of Raven which sort of, in our opinion, sort of make it well suited for this kind of application is, of course, yeah, so one of the features is that we do curtail Iris's higher order features, and I mean, so of course we lose out on expressivity, but I think it makes things conceptually simpler for the user, um, right? And we do have higher order modules, like I said, like I showed you, the stack with the parametric type and things like that. So does get us some of the thing back. Encode separation logic into first order logic, high degree of automation. I mean, of course, Z3 is great. Okay, so then the other thing is in the front end, we have what is called user-defined resource algebras. Resource algebras are essentially monoids with some more structure. You have a validity operator and so on. Um, and the idea is that in Iris, as opposed to what you're so in Viper, heaps have this fractional notion of sharing. Whereas in Iris, the program logic world, people have moved way ahead of that, and they've defined completely uh, novel monoids, these resource algebras, which are very useful in sort of modeling these complex proofs. And so in Raven, I mean, maybe I can, okay, maybe I can show it at the end, but we have a library which defines an interface called resource algebra. And the user can define their own resource algebras as long as they implement that interface. And the interface also, has all the checks like to make sure that your definition does follow all the algebraic properties, etc., and so on. And of course, we also have these higher order combinators like products, or I don't know, like authoritative resource algebra, whatever. The specifications are not that important, but we have a lot of these combinators. So basically, you don't always even need to implement your own custom resource algebra. Oftentimes, you just pick up a few components, you plug them in the right way, and then you can just start with your proof. And like I said, like I demonstrated, we also have a VS Code extension with some basic like LSP support and so on. Yeah, okay. Just to sort of wrap up a bit and yeah, start wrapping up and sort of give context about the tool. Yeah, it's implemented in about like 16,000 lines of OCaml. We have lots of like data structures from like the multiprocessor, like the art of multiprocessor programming book, and other data structures in the canon, in the literature. Yeah, some numbers, I guess. Yeah. Okay, so there are two tables, of course, right? The first one is basically we took so one of my collaborators and CMI alumnus, Nisarg Patel, who was also, Thomas's student, and we collaborated on the project together. Um, yeah. Sorry. So basically, he had developed, this technique of templating these data structures. So basically, if you look at the class of data structures that are commonly used, you would notice some patterns, right? And so his idea was that uh, I mean, prove the correctness of the template separately, and then the template has an interface which allows you to see or express like a Triber stack or a Michael Scott queue as that template instantiated in the right way. And so the proof of the template was done in IRIS because that is again highly concurrent code. Whereas the proof of the fact that a data structure satisfies the template invariant, that does not require separation logic. In fact, it will be quite onerous to do. And so they use another tool that was also developed by my advisor Thomas Weiss, called Grasshopper. So yeah, so that's the context for this table. Of course, I mean, Iris, the proof overhead is a lot, and so is the runtime, because for every proof, the compiler is checking every single proof step and making sure that at the end you get a QED, etc. With Grasshopper, the number of proof, like the proof overhead is much more comparable, but we are still faster because, I mean, yeah, I don't know, like I guess we have a leaner SMT encoding or whatever. Diaphragm on the right is an automation library for the Rock implementation of Lean of Iris, right? So basically, what it does is it does a tactic search over the entire space of whatever with a lot of heuristics and so on. So of course, you can see that the runtime just blows up because that is a much harder problem to solve. Um, Right, and this is averaged over a set of 23 benchmarks. I also have the entire table in the backup slides if needed. Okay, so that wraps up like most of my like the standard presentation. And then like in the past like few months, we also like there were some other works in progress that we've also wrapped up. I can quickly tell you about that. So the first thing is extension API, right? And yeah, I mean the idea is that if I were to implement some other if I were to want to do say separation logic verification on a different hardware architecture, right? Raven has a few built-in atomic hardware primitives, but if you want to define your own, it would be quite tricky because you would have to build your own sort of like pipeline, etc. Um, Encode the semantics of your atomic primitives in Raven, make sure that everything works fine, you don't cause any soundness issues in your encoding, etc., etc. Right, so that is a lot of effort that is wasted, especially if you don't like if you're just using it for verification and you're not not you don't really need a like a there's not like a specific front end language that you're targeting. And if you just want to, do it like for pedagogical use or like just experimentation or just to sort of prototype different things, having to implement things is a bit cumbersome. Having to implement your own custom semantics for everything is a bit cumbersome. So we've added like an extension API, etc., which allows you to directly, you write like 100 lines of OCaml code. You change a few parameters here and there in the compiler. You compile Raven, and then you have a language with custom commands, expressions, types, etc. Yeah, rapid prototyping, reusing existing database as much as possible. So to sort of demonstrate that, we took the probabilistic programming logic Eris, which is built on top of Iris, which took many collaborators and like months of effort. Yeah. And of course, like what they've accomplished is something greater than what Raven does. Raven does not have, foundational soundness, for instance, right? But you can sort of like it took me literally an afternoon to add these ec.rand, ec.contra, these commands to sort of be able to prove up an example, write up an example like this. So what this says is that so basically we take two random numbers from 1 to 10 or 0 to 9, whatever. And it says that if we have 0.1, like 0.1 error credits, which is this notion of, you're allowed to error out this percentage of the time, then the rest of the 90% we will return true. And I mean, basically what we return is, if the two numbers are equal, we return false, otherwise we return true, right?
Kansh,
And yeah,
we are roughly at 7:55. We can run
okay,
over by
yeah,
5 more minutes, but just wanted to give you
yeah.
an update on time.
Yeah, perfect. Yeah. And okay, so that's the example. And I mean, this is sort of how the system is architected. So, I mean, this is sort of the standard Raven pipeline: passing, type checking, atomicity analysis, rewriting, verification, and then the result. And the verification interfaces with the SMT solver. And we've implemented this whole system on the side, uh, which plugs into these extensions, which plugs into these hooks, and the extensions are built in a way that you can stack them up. Okay, so you can develop very small individual extensions, and you can instantiate Raven with whatever set of extensions that you desire. And in fact, some of the things that I've already shown you are implemented via extension. So in particular, the hardware primitives that I keep talking about, they're not, part of the sort of main library of code. They are implemented as an extension, and we have like 2 or 3 extensions that we load every time by default. And then the user is, of course, I mean, Raven is open source, etc. You can just clone the code and like fork the repo and build your own extensions or whatever. Yeah. Okay. And then the final work before I start to summarize is we've also worked on mechanizing the meta theory of Raven with respect to Iris. So what that entails is, I mean, the details are less important, but essentially at the end we get a theorem which says effectively that any property, any specification that you prove in Raven, there is a translation that translates that specification into Iris, and it says that the translated specification on the Iris side is also provable, like is also valid. So basically that sort of grounds Raven's soundness a little better. Of course, we don't get foundational correctness for each program that we verify, but for the overall system as a whole, we do get a higher confidence in the formal correctness of it. Okay. And yeah, now just to summarize, I mean, I guess, concurrent separation logic, which encodes everything into first order logic, a lot of good automation. We worked on the user experience a little bit. Great benchmark. Yeah, simplifies Iris. Additional front ends, I guess. That's for the future. Uh, yeah. Okay. I think that's my final slide. I have a few backup slides if needed, if it comes up. But yeah, that's about it.
Thank you, Ekansh. We can take
Yeah, of
questions
course.
if there are any.
Mhm.
Can you go to the probabilistic part once? The last you mentioned.
Yes.
So here, can you please say what are you ensuring and how are you ensuring that a bit?
Yeah, of course. That's great question. Basically this Eris logic. So I mean, the idea behind the Eris logic is you want to prove properties like cryptographic primitives that you won't have hash collisions more than like whatever epsilon percent or with a probability of more than epsilon, etc. So the way that they model that is they have a new separation logic resource which is called error credits. And I mean, this is continuation of other lines of work. So, for example, there are like these time credits, there are error credits. This is like a standard pattern that has shown up in Iris style separation logics. Because the idea is that the notion of ownership of resources is actually really flexible and very useful. So having error credits means that you're allowed to violate the post conditions but only with a probability at like with a probability lesser than equal to the amount of error credits that you have. Okay, so in this case, that means that at most 10% of the times I might return false, but at least 90% of the times I will return true. Okay. Yeah, and so I mean the program itself, you just randomly sample two numbers from 0 to 9, um, right? And if the numbers are okay, another thing I should clarify is that the lines in green are ghost code. So I mean you can ignore them for now. They should be relatively easy to follow along, but yeah, I mean whatever, right? So basically we look at the numbers that we are sampling. If they are equal, we return false. Otherwise, we return true, right? And intuitively, it's pretty easy to see that 1/10 of the time I'll return false, and 9/10 of the time I'll return true. But then how do you specify that? How do you prove that? Um, to solve that problem, the people over at Iris HQ, whatever, came up with the error credits, right? And that's the specification that I've proved. Does that answer your question? Is there any other lingering doubts?
No, no, it is fine. I kind of got the idea. Thanks.
Yeah. Okay. Thanks. Of course.
Are there any other questions or comments? Seeing none, we can conclude. Thank you for this talk, Ekansh.
Yeah, of course. I mean, yeah, my pleasure. Of course, like, connecting with like the Indian